Hello. Hello. Oh, can you? Hello. So you're all on mute. You don't have to be on mute for the hello. You don't have to be on mute at all. Good afternoon, Sylvie. Thank you. She wins. She wins. Hello, Kayla. Oh, and I think Kayla just sent me something I didn't see. Sorry. Hello, hello. Whatever you said, Kayla. Sorry. The answer is yes. I couldn't see it because I was teaching another class, but I saw there was something. Sorry. Okay. Hello, hello. I shouldn't say the answer is yes. I don't know actually what you said. Okay. Yeah, hello, hello, Sylvia. Hello, Kayla. Hi, Dylan. Hello, Jonathan. Hello, Marina. Hello, Abby.
Hello.
Oh, hello. Oh, she got voice. Boom, boom. That's points. My son.
A
Okay.
million points.
A million points. Exactly. A million. There's no limit. All right. Awesome. Awesome. And great, great. And hello, Ashley. And Kayla gets a million points for being sympathetic for the fact that I haven't read her email yet or whatever, which I just outed. Sorry. I know it was just a solicitation for funds. No, okay. Oh, we all okay. Who else did I not? Oh, and Giselle. Hello, Giselle, and hello, Remy. Well, I could have sworn I saw in 3D a second.
Hello.
Hello. Oh, that's Giselle. Hey, all right, Giselle. Yeah. Awesome. That's a million points right there, too. That's awesome. Wow. We need a lot of zeros not zero. You know what I'm saying? All right. Awesome. Awesome. Oh, more people. Hold on. Let's see. Let's see. Okay. Excellent. We have another riveting class. And and there goes the board. Of course, as a way of telling us. All right. The board was a foreshadow of what we want to get to today. I want to continue going over the homework. Of course, I want to, and I don't want to assign anymore because I know you guys are ahead of me now, which is good. So we're going to take a while to go over these things, and and again, just to make it clear, anything that has been assigned, if you did it, if you made any reasonable attempt by the time that it was actually due, then you already got a huge starter set of points. You may or may not have gotten any kind of detailed feedback, but you got a huge starter set of points to acknowledge your draft. And then but now everybody still has time to update and revise and improve based on anything we do in the lecture, and you can still get all the remaining points. And even if you didn't start, you still can, et cetera, et cetera. Bottom line is you just keep going from where you're going and keep going until you get all the points. Nothing new will be assigned for next Wednesday. I need to catch up to you. Hold on. I also have to fix this board. Hold on. Sorry. So we're just going to keep going and talking about the homework as we proceed. But as you might get, okay, so here, right. So the things I want to get to in one form or another are right here on the board. That's what I want to get to today. But I actually don't want to leave that up for too long because, interesting. Yes, I think that's true. Wait, that may be true, and we may have to talk about that. No, fair enough. And in fact, wait, which homework? What? That you may well be right, and that may be yet another reason why we need more time with it and more generosity on my part. Hold on, let me just.
Is it okay if we stick to algebra based? Because I know for a lot of us, we haven't done calculus in years. Like in my case, I haven't really done calc in about 10, 11 years. So when I saw that, I was like, oh, this is calc.
Wait, I totally understand. We do have to. This is a thing that we have to address every year in this class. I do understand what you're saying. I'm all sympathetic in all years. I want to address that. Let me just look at the homework for a second to see what we're. Oh wait, but wait, unless I assigned the wrong homework. Wait a second. Actually, though, I'm with you, and we have to talk about all that. But sorry, but wait, but to be honest, though, wait, homework. Are we talking about the same homework though? Like, I'm totally sympathetic to this point, and I do want to address it, and I want to make sure we have as much time as we need to do any homework and to get it right. But if I'm looking at the right homework, I don't see calculus. Wait, are we talking about the same homework? Did I assign the wrong? I'm looking at homework 2.
Oh, I meant like the lab mainly because the lab had the cosine, that type of stuff.
Wait a minute. All right. So yeah, we're definitely and you're also right. No matter what you say, you're right. Like I'm definitely want to hear all this, and we're going to make this work, whatever it is. And yes, in fact, you're correct that I wanted to just address where we were with the homework or address the fact that it's all going to be okay. But before we literally go over the homework, you're right that what I really want to talk about first is the lab. Absolutely. So I will hear in detail everything that you're saying, and I will adjust to whatever I need to adjust to. But I do have to ask, or I do have to say, I mean, you're definitely right that the lab and the homeworks absolutely involve cosines. Oh, yes. And I'm totally prepared to teach those from the ground up if need be. Often I do. But are we calling cosines calculus? Is that what I mean, I don't mean that as a criticism, but is that what you guys are? I mean, just to be clear, like we're talking about the cosine business. Is that what you are all? You're allowed to be concerned about that, and I will address your concerns. But I just want to get the vocabulary straight. Like we're about to be all about cosines, even if it means I teach it from scratch, which is fine at whatever pace. But is that? And maybe you could put in a direct chat if I'm making people uncomfortable. You could put in a direct chat, but is it the cosine stuff that you're talking about? Wait,
I think the last time I saw it was calc, which is why it made me think of calc. And then like a lot of people in lab were also like, "Oh, this seems like calc, or this reminds me of calc."
Oh, okay. All right. Just to be, and again, as long as we're all trusting each other here that this is a safe physics space. So again, no matter what we're saying, I'm definitely sympathetic to the math concern. Like, look, honestly, I could put, well, I'm sympathetic to the math concerns no matter what. And honestly, no matter what we say, my ultimate attitude about this class is that I don't that we're not doing physics without math, whatever the math is. Okay. So let me just get this straight on larger level. Physics definitely involves the language of math. No matter what physics we do, we're going to do the language of math. That's the bad news or the whatever news is that like we do need to deal with math of some kind. The good news is, in my heart of hearts, do I expect you to come in command of whatever math we need to do this physics? No. Am I prepared to teach from the ground up whatever math we need to do this physics? Yes. Do I think you can learn it with me to do this physics as long as we do it at the right pace? Yes. So I guess a corollary, the good news is I'm not actually expecting anybody to have any particular math, even if technically it was a prerequisite. I mean, I'm expecting people to have seen things, like been exposed to things. I'm not expecting anybody to be in command of things. Even people that think they are or say they are often aren't. I'm expecting that we're willing to do things together to learn the math, whatever math it might be, that is needed to do this physics. In fact, secretly, honestly, what I really think about all these physics classes is I know technically they all have different math prerequisites. We tend in this country to say you need a certain level of math in order to get into a certain physics course. Honestly, in my heart, I really think it works the other way. I honestly think that the big purpose of physics classes is that it's a place where the math actually becomes real or alive or motivated or enough contextualized enough to actually start learning it. Like whatever math I do know personally at this point, I actually didn't get it at all until I started working it through in a physics class. So on the good news and the bad news is I don't actually expect anybody to be on top of anything when they walk in here. The bad news is I expect with me that we can all get on top of this together. I think physics actually provides that context and that motivation for doing so, especially if we're willing to do it at whatever pace we need to do it, to do that. Okay, so hopefully that's my larger math message. And this message, someone's here, but I can't let them in. Hold on a second. I see that someone's here, but I can't. Hold on. Or I think someone's here. Oh, there they are. Okay. And I'm saying this like this is a speech I could have given you even before you said anything. And I also, to be honest, again, I give this I give this speech in Physics 204 as well, where they're like literally required to have calculus classes to take that. But even there, I don't really expect that they understand the calculus at all. I teach it from the ground up with them, blah, 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 blah. So what we're doing here, whatever you need, we're going to do. And I'm prepared to do that. That's like my larger thing. Now, to be a little bit more, and that's really what today I'm planning on doing. I figured that was going to happen. And hopefully that puts some minds at rest. Like, we're not going to, in other words, again, we are not going to walk around the math, but we're not going to expect that you already have the math. We're going to walk through the math, into the math, together, holding hands and singing Kumbaya if necessary. And I'm being cheesy, but I am serious. Now, to be more specific, I will say trig, cosines, sines and cosines. Yeah, that comes up a lot in the lab. It comes up a lot in the homework. Oh, yeah, we need the sines and cosines to go on like we do. We literally do. Is that something that most people bump on? Is that something that people have maybe sort of gotten through years ago and kind of gutted their way through, but never really knew what they were or what they were doing? Probably. Like, sorry, my son's telling me quiet. Like, if sines and cosines give you a bump or make you uncomfortable or bring back bad memories or make you feel like, sines and cosines, I'm with you, and we will. You have to be with me that we will do them, but we'll do them from scratch if necessary, and I usually do. But now, just to be technical for a minute, I think cosines and sines might remind you of calculus because they come up a lot in calculus for sure. But really, sines and cosines are not themselves a calculus thing. They are like a trigonometry thing, which is generally taught like in algebra 2 classes or whatever. Like, just to be technical, I think sines and cosines is something that everybody has seen somewhere before they took this class, or it is technically in the track for this class, I believe. And you stop me if you think I'm wrong, or stop me in the direct chat. But yeah, if you don't like sines and cosines, we're going to deal together. Just like wipe your mind out, get rid of all your bad and good. Assume that I'm not assuming any good memories of you, but get rid of your bad memories, and we will do them from scratch. But yeah, but I don't think they are calculus. And yeah, we do have to do that. So wait, it was okay. I'm looking at okay. Thank you. All right, thank you and really tell me in direct chat if you want what like I was honestly going through. But thank you, Marina. I appreciate that. Yes, I'm saying, and thank you, Giselle. Honestly, I'm saying what Giselle's saying, like, I think cosines are algebra 2/trig. That doesn't mean you like them. And it doesn't mean you mastered them. And it doesn't mean you ever wanted to see them again. But it does mean technically we are. Like, that is the level of this course. I'll even go out and one more limit and say, I know most people I know that did not in their lives go on and pursue like a career in a math or science-based thing. Most like super intelligent people I know, most people I know are super intelligent and who have a career. Most people stopped liking math around trigonometry. Like, I know trigonometry is the cutoff point for most super reasonable people. There's something about it that is a big turnoff. I totally get that. And I'm hoping here to maybe like give it a fresh start with all of us. But yes, we definitely do have to deal with cosines. And these labs and everything are designed to maybe give us a physical place to hang our hat with cosines and sines. Okay, but thank you, Marina, and thank you, Giselle. Okay, I'm looking at okay. Fair enough. And thank you for your honesty, Eugene. Like, that's a very honest thing to say. And again, this is also why you're totally going to get at least another week to do that homework, like at least. Why everything is a draft and a work in progress, why no curtain is going to fall on that. Because I think that Eugene is probably right. And it wouldn't be the first time that you might look at that and go, oh, this is calculus. And then not only like shut down mentally, but you might also legitimately say, wait, we're not supposed to have to know calculus for this class. So you might say, wait, this was a mistake or whatever and stop. Now, right, true. So fair enough. So we're gonna have another week on it at least. But yeah, I am here to say it's actually not calculus. It actually is trig. And secretly, if we do enough in this class and we get together on this, the fact is you could end up learning calculus by accident from this class if you look the other way and you just relax and you don't call it calculus. You might end up learning more calculus here than you might have anywhere else. if you're willing to. But yes, but we don't have to. That was not calculus, it's trick. Okay, I think wait, it's okay. Eugen, thank you. Marina, thank you. Giselle, thank you. Okay. So all right. My agenda for today, if we didn't have a lab to talk about or anything, my agenda is actually to teach you what a cosine is. Sorry. Okay. My agenda is, and this is a big part of the agenda in Physics 102. 102 is the secret place where we actually try to do a last-ditch effort to get people to understand cosines. It's actually half the point of the course. You guys are not alone in sort of wanting that. And I'll even tell you right. Well, so that's what we're going to do once we go to the lecture material. However, first, oh wait, there's more in the chat. Sorry. Oh, okay, cool thing. Sorry, well, I'm just laughing. Wait, okay, wow. Okay, see, this is why I love this class, and I love my son, and my wife, and my dog. Because all right, wait, I'm going to turn off we don't even need the board for this. Hold on a second. I was fighting with this board. We don't even need it. Give me a second. Because we're going to talk. We're going to make this time fly, ladies and germs. Hold on. How do I turn this off? Okay, yeah. Even my dog heard me say cosine and started crying, like literally. Okay. Oh, she is crying. The dog is kind of crying, but it's partly because I mentioned cosine. Okay. So wait, I want to respond, but I'm laughing. I'm not laughing at you. I'm laughing with you. So what Remy said in the chat, if I have to open up a unit circle, I'm going to cry. All right. And Jonathan, thank you, Jonathan. First of all, you all should submit. I hope you all realize there's a million participation portals. Oh, wait. So do you guys want me to? Okay, I'm going to say something to all of you in a moment because we're all kind of. Oh, okay. So, first of all, I hope you all remember, like Eugen, Marina, Giselle, Remy, Jonathan, who I'm very happy to hear from, Dewin, all of you, even that emoji. Like, there's probably 3 portals you could submit that to for class participation points. I'm not kidding. Like, please triple dip. Like, all of you are helping me. If nothing else got accomplished in this course, but that you guys were honest enough to me to say that we actually need to change our relationship to the unit circle, and if we could actually even vaguely come close to accomplishing that, it would be money well spent, honestly, because you're all going on in science. And sadly, you're going to need the unit circle. It's a real thing. It really matters later in science. Like, unlike some things, like, okay, factoring a trinomial or completing the square. Okay, yeah. Have I ever used them in my life, except when I'm tutoring something? No. But the unit circle, oh my God, no, depending on where you go on, it's a really real thing. So I'm laughing because, yeah, did I like the unit circle the first 400 times I saw it? Absolutely not. I hated it almost as much as I hated graphing, which I hated even more. But if you can trust me, that I trust you, that you're not crazy for hating the unit circle, I totally get it. And most people I work with start by hating the unit circle. But if you trust me, that there's a way to become more familiar with the unit circle and at least be comfortable with it, if not affectionate toward it, I think we can accomplish that together by the end of this class. Like, I'm laughing. I'm only laughing because Remy hit the nail on the head with both aspects of that statement. And then Jonathan and Dewin hit the nail on the head with both aspects of their emojis and their modifications. Like, the deal is, yeah, unit circle. I'm sorry. That's exactly the land that we're going back to here in this class. We are. But yes, it's because I know that everybody hates the unit circle. I don't have any illusions about that. But it really is a thing. We're gonna look at it fresh. Maybe we'll call it something else just to give it a fresh start. Maybe will I start right now? Okay, you know what? No, I am going to start right now. I want to totally hear about the lab, of course. I want to talk about but you know what? I'm going to use this as a jumping point right now. I'm not saying this to get in the ring with Remy or anybody else. I assure you. I already know all of you enough to know that I want to stay on the same side as you in this discussion for the rest of the semester, because I know it's fun to be on the same side as all of you. And I can only imagine what it would be like to be I don't want to be on the wrong side of a fight with any of you, especially not about the unit circle. So look, I'm going to start right now with the lecture material that I was going to do. Okay. Like put aside the homeworks. Like don't worry about the homeworks. Don't worry about grades. Again, just assume right now you're getting a good grade and that this is an opportunity to learn some stuff that you hated until now. Okay. And that I hated until I didn't. So what I'm going to do, we're going to start from scratch. So this is just lecture notes. We're going to take notes. I'm going to put the board back up. We're going to take notes. It's not going to be a whole unit. I'm not going to draw a whole unit circle thing with a million labels on it. Don't worry. I'm not going to ask you to memorize all that. Don't worry. Just we're just going to start radians and cosines from scratch. You'll see. We just get the board going and we're going to go. So this is lecture period right now. Then we'll get back to the lab. I just got to get the board going. Come on, if the board ever goes, if not, it's going to be fascinating. Wait. Yeah. No. Oh, Salady. And now Salady said, see, we're all part of the discussion. This is such a great class. You're all, even if unified hate motivates you all to participate, fine. And yeah, I'm not asking you to memorize. I can tell you right now, when I talk about the unit circle, which I'm not going to at first, but when I do talk about the unit circle, I would want you to memorize one value on it. My claim to you is if we understand this well enough in a fresh way, by the time you get to the unit circle, if you just memorize one thing on it, all the rest will fall into place. I'm not going to ask you to memorize them, believe me, but that's funny, Sue Lady. You suffered. No, we're trying to end suffering now, but I'm suffering now because my board's not working. Give me a second. I don't know what's going on. Hold on. But believe me, I've been here before. Believe me, I have. Here we go, board. I'm just trying to get the board.
Opens in a few minutes, I'll take you out.
Hopefully the board's about to come. Yeah, there's the board. Okay. Oh my God.
Thanks.
Okay, here we go.
Have more, please? Honey, give it a rest. You just had 5 pieces. But 6 is a charm. Yeah, I hear you. Just hang tight.
Here's the deal for starters. Okay, cosine is a function that we apply to an angle measured in radians. Okay, right? That's a straightforward statement. But even that statement alone, let me get straight. I know even when I just said that or when I just wrote that, like 5 people shut down emotionally. I know that. Like I'm sitting here going, I'm going to explain this. Wipe your minds clean. I'm going to give a fresh start to all this. Okay, here we go, guys. And everybody's ready. And we're like, okay, maybe we'll actually get it this time. Okay. And then I say, it's like a typical math teacher. I say, cosine is a function that applies to an angle measured in radians. And if I were you, I would like lose all faith right there. Because first of all, I never liked the word function. Like even if I understand the word function, it certainly doesn't excite me. It certainly means something really boring is about to come. If I'm like many people or like, right. And then second of all, I say it's applied to an angle measured in radians. Now radians is a huge turnoff. Radians is where a lot of people consciously are like, okay, that radian stuff, like even function, at least I thought I understood, but it was boring. Radian, I don't even understand. Most people, even people that use it and think they can get answers right and have gotten used to radians, have gotten used to it because they're like, I've just accepted it. Like it's not meaningful. It doesn't mean anything to me, but I sort of know how to use them. So like I know how to convert like pi over 180 equals blah, and I do it on my calculator. But even most people, and I mean most people who use radians have long since stopped even trying to make any sense out of them. They just use them. And so I know that. So what I'm here to do is break down these words for you. First of all, I will tell you right now that radian is a measurement unit for angles, but the real reason that most people shut down when they hear any of this stuff, when they start doing any trigonometry, even before they get to the unit circle, the real reason most people shut down is actually that most people don't know what an angle is, except that most people think they do. So there's a disconnect. I'll tell you what I mean. That looks like an angle, right? When people say, for the longest time, like I honestly, like I would say about 15 years into my teaching career, let alone my student career, for about 15 years into my teaching career, when people said angle, I would picture something like that. I would picture two lines intersecting at a point. And if they said angle, I thought they basically meant like how much space there was between those two lines. Now, I'm not saying that's wrong. I'm not saying it's wrong. If that's what you're picturing, you're not wrong. But that's a dead end way to picture an angle. It's actually a super deceptive, unyielding way to picture an angle. It's really not helpful when you start talking about what it means to measure an angle. Okay, the first confusion is people tend to think that angles are spaces between two intersecting line segments. And so when someone says, I'm going to measure an angle, or if they say this angle is bigger than that, most people, or at least I, always thought to say that an angle was, let me just draw it here. Like here's three angles. I'm not saying these are not angles. I'm not saying anything is wrong. I'm saying it's much less helpful. That there's a more helpful way to think about things. So I'm saying, look at these three angles. In my mind, these are angles, right? And if someone says, and I think you all know, I mean, I can ask you, but I think we'd all agree, like the third angle is probably biggest. The first angle is like medium, and the second angle is the smallest, right? I mean, I think, first of all, is everybody, yeah, okay, all right, thank you, jjP, awesome, okay. But so it seems like, so we consciously think we get angles, okay, I know what a bigger angle is when someone measures and says that's a big angle, they mean that. But now look, here's the thing. That means unconsciously, we're thinking that an angle is like the space between two intersecting lines. And when someone says an angle is bigger, we think that means, okay, there's more space between the lines. Like we think it, like if you look at that picture, it kind of seems like the reason angle 3 is the biggest is because the one line is farthest away from the other line, right? Now, again, I'm not saying that's wrong, but that's actually really confusing in the end. That's really confusing because if you say, and it really doesn't help us do anything with angles to think of them that way. If I say that measuring an angle is measuring the space between one line and the other, or let me say this again. If I think that an angle is an intersection between two lines, and I think that measuring an angle is how far one line is from the other, that leads to a lot of problems. Like, okay, like how far is this line from this line? I don't know, like I guess it's about this far. Like I could put a ruler there. It's like about this far, right? Whereas this one is only about this far. So I guess this third angle is a lot bigger than the second one. But wait, that right? That like the angles, the lines are farther apart in the third angle than in the middle one. But no, like that's what my brain unconsciously is doing. If it's thinking, okay, those lines are far apart, it's a big angle. So I'm thinking like, yeah, they're really spread. There's a big distance between those two lines. But that's really problematic. That's not really what an angle is about at all. First of all, if by far apart, well, I'll say it and then I'll write it down. I'm saying, first of all, if the bigness of an angle is how far apart the two lines are. And if the far apartness of the two lines could just be represented by that blue dotted line there and by like a ruler that I could put down between the two lines, then why aren't I just using a ruler? Why aren't I just talking about distance? Right? If the size of the angle is how far one of the two lines is from the other, then that's not anything different from just saying length or distance or displacement. Like that's not a different measurement. That's not a different thing. So anytime someone walks in and starts talking about degrees or radians, God, heaven forbid, if someone starts talking about radians, your conscious brain doesn't reject it. Your conscious brain's like, okay, I guess they know what they're talking about, radians. Okay, I'll accept it. I'll do it on the test. But your unconscious brain is going, what the heck is a radian? Why aren't they just talking about meters? Like, why aren't they just measuring how far that line is from the other line in meters? Right. And so the whole package just gets like, at least that's what took me years to realize. That's what my brain was doing. I can't speak for yours, but my brain didn't accept these radians or anything because really my brain was just visually looking at how far apart one line was from there and going, well, yeah, that line's far apart from the other. It's like 3 inches rather than 2 inches. So I was really just thinking about distance, and I didn't understand what all this unnecessary other stuff of radians was. I could have just said inches. So okay. So point number one. Okay, what I'm trying to argue right now, again, I'm not saying you're thinking anything wrong. I'm trying to like recalibrate how we picture an angle. So first thing I'm saying is I'm trying to recalibrate how we picture the idea of measuring the size of an angle. So the first thing I'm saying is don't measure the size of an angle by picturing how far one line is from another, because then you're just picturing farness, distance. That's not picturing what an angle actually is. So I still haven't told you what an angle actually is. I'm just trying to address what it isn't. The second problem with thinking of an angle as two lines that are intersecting and thinking of the measurement of the angle as how far apart they are. The second problem is that someone's here. Hold on a second. Okay. Hold on. The second problem is it's the second problem. And this is leading to ultimately a definition that we actually do use. But the second thing I want to say is, even if we're picturing an angle as a V, and when someone says it's a big angle, we think, oh, it's a big V. And we think something like, okay, it's like how far from, one line there is to the other line. In other words, even if you're starting to think in your mind a modification that I could make of that blue dotted line, even if you're starting to think something like, well, maybe you need what? Yeah, pardon me. Hold on one second. I'm sorry. I mean, class, pardon me for a second. I'm sorry. Well, because I'm the class. Wait, here's a flip. I don't know where you have to go. I apologize. As you may have gathered, certain schools that are not called John Jay are on vacation right now. Okay. So far I'm saying, and please bear with me again, I'm trying to talk what's not true, because I think it'll help us start again and get to what actually is true. And also tacitly, what I'm really saying here is cosine is something you do to an angle, and I think angles are completely, like, I misunderstood them forever, and it held me up, and I didn't know that's what was going on. I thought I understood them, but I was blocked because I didn't. So the second thing is, even if you're following, if you're like, all right, yeah, like you can't just like draw a straight line between two lines and call that the distance of the angle. Like even if you're following me and thinking, okay, but couldn't you maybe draw some sort of curved line or something, like, which is what we're going to do. Like, even if you're thinking, okay, now how far apart the angles are, it's like how far apart they are. And when you open two lines, they sort of open in a curvy kind of way or something. Like when you open scissors, right? Like they somehow open on an arc or something. Even if if you're not thinking that, don't worry about it. But if you are thinking that, you might be thinking, shouldn't you draw some sort of curved line from one to the other to talk about how, and isn't that why we do that when we make the theta symbol? Well, then you're onto something, yes. But then I would still ask, the problem still is, where are you going to put that line? If you want to, when you say that this angle number 3 is bigger than angle number 1, we're trying to say in some kind of a way that those two lines are more spread out than the two lines of number 1. But like, where? Like, we can all tell that part of the problem here is that if I trace out, if I just measure right here, if I measure right there in angle 3, whereas I go all the way out here in angle 2, then angle 2 looks bigger than angle 1. I mean, than angle 3. Now, we know angle 3 is bigger than angle 2, and you know that too, right? I mean, everybody intuitively can see that angle 3 is bigger than angle 2. But if you really start talking about like what we mean by that, or how you would measure that, or how you would prove that, like the procedure for actually measuring an angle starts getting very dicey if you think about it as drawing some kind of interval between the two lines, because it totally, first of all, if you draw a straight line interval, then I don't even know what we're doing. We might as well just be measuring distance. But second of all, even if you draw some sort of curvy thing, if that helps, where you draw it makes all the difference. If you draw it too far out on the angle 2 looks bigger or would register a bigger measurement than angle 3. So we've got to have some consistent, that's not what we're talking about. In other words, there's got to be some consistent rule or some consistent procedure for actually showing ourselves what we mean when we say angle 3 is bigger than angle 2. I'm going to say this one more way, and then I'm going to pause and make sure I haven't proven anything. I haven't taught anything. I'm trying to unteach something before I teach it, okay? What I'm trying to say right now is that it's not clear. Well, what I'm trying to say right now is that if we think of an angle as being an intersection between two lines, and we think of the measurement of the size of an angle being some kind of distance of one line to the other, then we're not saying anything meaningful. And no wonder we're all confused and hate trig, because this doesn't make any sense, right? And frankly, I probably felt like it was what my teachers were saying, and so I turned off to it for a long time. It doesn't make any sense to think of angles this way and to think of measurements of angles being this way. I need some kind of procedure by virtue of which I could show you quantitatively that one angle is actually bigger than another angle. If I could come up with a procedure that could show you that the measurement quantitatively of one angle is bigger than the quantitative measurement of another angle, if I could show you that procedure, not only would that be more satisfying and more clear, but it would also mean that we actually have a clear idea in our heads of what an angle and angle measurement is. So before I do, so that's what I want to do. And before I do, okay.
Hello.
Okay. Hi. Okay. And that is that. Yes. Okay. Before I do that, since there was a beat anyway, can I just, I'm not saying I've explained angles yet. I'm just explaining what angles are not. But can I see an electronic hand or anything of who's with me so far that this is what, am I making sense so far? The angle is not thank you, Jake. All right. Thank you, Giselle. All right. Awesome. And thank you, Marina. Okay. All right. Awesome. So here's what and thank you, Kayla. So, and thank you, Jonathan. And thank you, okay. And thank you, Felix. Yes. So here's what I submit to you, then an angle is not an intersection between two lines. It's often represented that way. It's often represented that way for good reason. But you know what an angle actually is? You know what it is, why it is that we actually know that angle 3 is bigger than angle 2? Actually, I'll ask, I'm going to tell you, I think it's something very explicit and very clear, and I think you'll agree when you hear it. But maybe do you know where I'm going with this? What is actually an angle? What is an angle?
I don't know.
My son says he doesn't know. All right. Oh, something in the chart. Oh, you do know. Okay, what is it? What is an angle?
I'm not spoiling it for the class.
Okay, my son is not going to spoil it for the class. And actually, I don't even disbelieve him. Does anybody want to take a shot? I mean, I don't want to bore you. I don't want to be redundant.
You do.
Okay.
Oh.
Does anybody have a thought of what's a different way we could picture what an angle is that would actually give us some objectivity and some quantitative procedure? And I'm not challenging you. If you don't know, good. I'll feel like I'm giving you your money's worth if I tell you. But does anybody have a thought first before I step all of? That means no. All right, I should go. Here's what an angle is.
We'll talk outside in about 5 minutes. What do you mean? If you want to come to me, you want to watch my body for a little bit? Just breathing. Yes, I would like to watch. Thank you. Everything on YouTube is trash.
Okay, this is so dumb sounding in a way. It may sound so dumb and sound like such an anticlimax, but honestly, like all great truths in physics, this is a very simple, seemingly self-evident truth. It sounds obvious once we say it, but it isn't obvious until we say it. And what truly isn't obvious about it is how much more helpful it is than many other seemingly self-evident truths. What an angle actually is a portion of a circle. Something just happened, sorry. An angle is a portion of a circle, of any circle. When we say that one angle is bigger than another, we're saying that we've carved out a bigger slice of a pie than another. And what we're really trying to say is we don't need to know how big the pie is. I don't mean pie like pizza. I mean, like, no, I really, no pun intended. I'm not trying to confuse things. Let me say this again. I'm saying an angle is a portion of a circle, such as a pizza. If I say, let's look at these two angles for a second, okay? The top angle is definitely bigger than the bottom angle, right? And I'm drawing them as two intersections of lines because that is the way people always draw angles, right? But what I'm really getting is if you really look at those angles and you see that the top one is bigger than the bottom one, more to the point, if you see that that top one is what we all recognize as a right angle, okay, forget pi over 2 radians for a moment. Forget 90 degrees for a moment. Forget any of those particular units that any culture has decided to consider when looking at those angles. That top angle, everybody recognizes is what we would call in English a right angle, right? Everybody knows that's a right angle, that top one. And everybody knows that's bigger than the smaller one because what we're really recognizing, if we tap into our unconscious, what we're really recognizing is that this top angle, what we're really saying is the top angle is a fourth of a circle, right? Like literally, that's what a right angle is. It's a quarter of a circle. A right angle, yes, is one vertical line and one horizontal line, but you recognize it even when they're tilted, right? Everybody knows, like, it's impossible to put in words. You know that right angle. It's when the two axes are like perpendicular to each other, right? When they're like, when they make like the corner of a square. But what does all that mean? It means that you didn't go, that the two lines didn't get fully opposite to each other and they didn't come back all the way around to be the same as each other. It means one line went a quarter of the way around from the other line. That right angle is a quarter of a circle. And here's really the depth of the point. We all know, like if I gave you a slice of pizza that where the edges of it were forming a right angle with each other, if I gave you a right angle slice of pizza, you would know that you just got a fourth of the pizza without ever seeing the rest of the pizza, right? You know, it doesn't matter if it was 12-inch crust or 16-inch crust or whatever. You know that's a fourth of a circle, irrespective of the particular circle chosen. This is the universality of angles. They are literally a portion, a fraction. An angle is a fraction of a circle. A right angle is always literally a quarter of a circle, no matter what culture we're in, no matter what units we decide to measure. And I don't care if you call it degrees or radians or whatnot. And most important, I don't care how big the circle is. The angle below it on this page is clearly smaller than the right angle, even if you don't know. Well, I don't care if you call that 30 degrees or if you know it's 30 degrees or 35 or pi over 6 or whatever. The point is, you know that angle on the bottom is smaller than the top because you know it would be less of a pizza. Like, you know, if you got that slice, that 5 others of your friends are going to get slices like that rather than 3 others of your friends or whatever. Right? Let me pause there. So first thing I'm literally saying, and this is not a joke, and it's also, this is not a trick to make things easier for you. I'm saying fundamentally, this is the truth. What an angle is a portion of a circle. In fact, I'm going to say one more thing about that. Historically, the Greeks didn't use degrees, and the Greeks didn't use radians. They didn't call a right angle 90 degrees. They literally called it a quarter circle. All their angles were literally phrased as Greek words that meant different portions of circle. And that's how they did the math. Like, you can do math that way because that's what an angle is. Wait, I'm going to pause for a second. First of all, do you understand what I'm saying so far? Okay, that's one person. Okay, sort of. Yeah. Okay, thank you, Silvo. You guys are right there. Okay, awesome. Yeah. Oh, cool. And then Soleil. I'm just getting so excited. All right. Now, that still doesn't tell you cosines. I understand that and all that. And it doesn't tell you about unit circles. And I'm not worried about unit circle yet. But I will tell you, you could start to see why the unit circle starts to come up and why this other stuff starts to come up. Because fundamentally, an angle is not an intersection. It's a fraction of a circle. Now, let's be more specific. So we're just building up angles here. Then we're going to build up radians, and then from them we'll build up cosines. And if it takes us a month, it takes us a month. And by the way, I literally mean, if it takes us 2 months to do a cosine, we'll do it. And you know why? Because it won't. Because it won't. As long as you're being as honest as you were being with me, telling me what you don't know, I know you're going to be honest with me and telling me when you do know it. And we always do take some time with this in this course. This is not the first semester by any means, but it won't take us 2 months to do this. It'll just take us a little bit. So that's what an angle is qualitatively. Now, talk about measurement. Oh, and by the way, and similarly, right? Like, and honestly, and I say this with all respect, like my 8-year-old son totally knows what a 360 no scope is, right? Like a 360 no scope, like they say in Fortnite all the time or something like that. Like, he knows a 360. He knows what a 360 is. He's never studied trig. He's never like crunched his mind around degrees or radians or anything, but he knows what a 360 is. Because what does he know? He knows it means a full circle. Right? That's what forget why we divided. We'll get to this. Why anybody ever decided to divide a circle into 360 parts. There is a reason, but you may or may not like the reason. It was just a decision. We never had to do that. The point is, what everybody knows when they say 360, what they've sort of gotten used to since 3rd grade, is 360 means full circle. 180 means half circle. 90 means quarter circle. That's the deal. That's what we're all picturing. So it's literal fractions. It's literal. Sorry. Oh, thank you. Oh, cool. Awesome. Thank you, Kayla. All right, I'll take it. I don't even know which connection you meant, but okay, no, great, good. And I am dead serious. And again, please understand, I'm not talking down to my advanced understanding of way more advanced things got way more advanced once this settled in my mind. It's talking up, not down. It's, you get my point. So Okay, so but thank you, Kayla. I totally appreciate it. All right, so an angle is a portion, and now portion's the English word. The more mathematical word for portion is fraction. And bear in the back of your mind that fraction means a ratio. We're going to get to that. But I do mean fraction. Like to say that an angle is big is to say that one angle is bigger than another is to say that it occupies a bigger fraction of a circle than another. And to get a fraction, like 1/2, 1/3, 1/5, whatever, 2/3. But also remember in the back of your mind, like the reason this works, the reason this is sort of interesting is the whole assumption that it doesn't matter what size the circle is, right? So right from the get-go, notice I'm saying like the size of an angle is not actually a thing like meters or kilograms or seconds. Like when we talk about the size of an angle and compare it to the size of another angle, whatever numbers we put to this, they're not standardized. Like there's a specific meter. And everybody agrees on how long a meter is. And then a kilometer is 1,000 of those. And 2 meters is clearly longer than 1 meter, right? Same thing with seconds, same thing with kilograms. But other things that we use in science aren't like that. For example, the word cycle, right? Cycle is a concept, but there's no standardized size of a cycle. A cycle could be a lot of meters there and a lot of meters back, or it could be a couple of centimeters there and a couple of centimeters back, or it might not even be measured in centimeters at all, right? So I want you to realize right from the get-go too that and this was whenever they used degrees or radians in classes that I took, I sort of took it for granted without consciously thinking about it. I took it for granted that degrees and radians were like meters or kilograms or seconds, that there was like a specific degree, like that 1 degree was a certain size in space or something that was a standard on which everything else was made. That's not the case. There's no such thing as the size of a degree or of a radian. They're English words that mean fractions of a circle that could be any size. By the way, no wonder this is confusing, right? I mean, it's abstract in that sense, but okay, but we could still make sense of it. So if an angle quantitatively is a portion, i.e. fraction of a circle, how do we quantitatively measure it? Right? This is our next question. We now, I think, all agree. Oh, sorry. Okay. We now all agree, I think, or most of it, that that's what an angle is. It's a portion of a circle. But now we want to put numbers to it somehow. I want to be able to say not only that this angle is bigger than that one, but I want to say this angle is twice as big as that one, but the other one is 1/3 as big as that one, right? So where do these numbers come from? What, like literally, where do the numbers come from? They come from here.
Ezra.
Okay. So here we go. What I'm saying is when we talk about how big an angle is, what we're really talking about, like I keep saying, a section of a circle. So instead of picturing lines intersecting, and of course you can see where the lines intersecting is coming from, because it's like the two edges of a slice of pizza or whatever are those two lines. I'm not saying two lines have nothing to do with this, but I'm just saying when you really picture how big a angle is, when you really picture how big a slice of pizza is, don't get distracted by the two lines. Look at the crust, right? The real point is we're talking about a big angle means that you've taken a big portion of the circle. The circle is this round thing. It's the edge of the pizza, right? One slice is bigger than another if it has a lot more crust, right? So at some level, we could just say, at some level, we might want to say, oh, the size of an angle is the size of crust, or put another way. Like, okay, like that red bit, that red crust, that's the crust that would be taken for a slice of pizza that was at right angle, that represented a right angle. And you could see that crust only, was that big. It went a fourth of the way around the pizza. So at some level, what I could just do, or what I might want to do, is just literally measure the length of that crust and say, okay, if that crust is that long, as long as the red line, then I've got a right angle. And if the crust is twice as long, then I've got, 180 degree, or whatever you want to call it, angle. I could just look at the crust. But here's where the whole depth of angles, the whole advantage of the concept of angle also becomes a disadvantage. The thing is, we said that an angle is an angle no matter what size circle you cut it from, right? Like, in other words, even if I had a pizza that was this big, right? Then, okay, I'm drawing, that was actually a terrible circle, but that red piece is also a right angle, but it's a smaller crust, right? It's also a right angle because it's also a fourth of a circle, but it's cut from a different circle, right? Both of those are right angles. We want some way of measuring things that captures the fact that both of those are right angles, and both of those represent 1/4 of the total crust of that pizza, but they are two different crust sizes. Well, why are they two different crust sizes? Because they're from two different circles. In fact, the outer crust is, let's say the outer circle is twice as big of a radius as the inner circle, right? Let's say the outer circle is a circle that is twice the radius of the inner circle. Well, then, in fact, that crust on the outside is going to be twice as big as that crust on the inside. So what we say to ourselves is, oh, yeah, right. This is the whole deal. This is why, like, if you want to, what we're basically saying to ourselves is, if we wanted to think of an angle as how far this line is from that line, the first modification we'd have to make on that idea is we'd have to measure along a curve, not along a straight line, because we're really cutting these things out of circles, not out of dead space. But second of all, we'd have to say, oh, we need a standardized rule for where are we measuring between the two lines? So what we say is this. We say that what an angle is by definition, an angle is the amount of, we say that if you measure the arc length, if you measure along the perimeter, if you measure the length of that crust, like if you literally put a string along the crust, like along the curvy crust, you took a string from one end of the crust to the next, and then you laid the string down next to a ruler, right? and looked at the numbers on the ruler, you would then have the length of that arc, the arc length of that portion of the crust, right? And you would have a measurement that is of length measured in meters, right? We're saying the size of an angle is how much crust it gives you, but per radius. I know you've seen this before, but put your bad memories out of your mind for 1 second. What I'm saying is angle really is intuitively crust length. The more crust you get, the bigger angle you have. But per each unit of radius that your circle is. In other words, if we had a circle, in other words, what I'm saying is you just measure this. If you want to know how big your angle is, you just measure the size of the crust, of the arc length created by that angle, but then you divide by the radius, because what we're in effect saying is like we're saying how much crust would we have gotten if we had a pizza of radius 1, a 1 unit radius pizza. We're saying angle, pretend we have a pizza of radius 1. Then if we want to measure angles in that 1 pizza, we definitely would be self-consistent by just looking at how much crust we get. Like a right angle, we get a certain amount of crust. 180-degree angle, we get twice as much crust. A full circle, we get 4 times as much crust, right? And we could be done. Just like comparing crust, we'd be comparing angles. So that could be our whole deal, as long as our radius was 1. But if we ever happened to go to a pizza that was twice the size, if we went to a pizza whose radius was 2, all the crust length measurements we would ever get would be twice as big, just because we were looking at a bigger pizza. So what we do is we say, you know what, from here on in order to measure angles, we're just going to measure arc length, and then we're going to divide by the radius so that we can have a standardized fair unit of measurement, so that it's as though we're saying how much crust would we have gotten if we were just in a 1 unit radius pizza. So at the end of the day, we're saying that an angle is a pure ratio fraction of meters to meters, right? Like we're literally saying how much crust did you get per each unit of radius you have. Once you standardize your radius, the more crust you get means the bigger angle you have. You're going to get 4 times as much crust if you go around the whole circle than if you just do a right angle. So an angle is literally a fraction of a circle. What fraction? The amount of crust you get, the amount of arc length you get per the amount of radius you have. Arc length is measured in meters. Radius is measured in meters, so the meters actually cancel out. So at the end of the day, when you talk about an angle, you're literally just talking about some ratio, some pure fraction that is just a number, like quarter of a circle or half of a circle or eighth. But where do we get, if it's literally a fourth or an eighth or whatever, we get it by dividing the meters of arc length by the meters of radius, and we end up with a pure fraction. Now, I still have to say a little bit more, but whatever number we would actually get, we're going to do a couple examples of this in a second. But if we just do it purely like that, the fractions that we get in a moment, we're going to call radians, just because they're just arc lengths that are normalized or like adjusted, calibrated, standardized to 1 universal radius. So these ratios, these fractions we're going to call radians, but I want to alert you before we even do any examples, radian is just a word like cycle. It just means a certain type of fraction. A radian is not like a meter or a kilogram or a second. It's not a standard size. It's just an English word for a fraction of a circle, derived this way. Okay, I'm going to pause for a second. First of all, we're going to do examples in a minute, okay? And I'm going to show you how it compares to degrees and whatnot. But also notice everything I've said so far. We haven't done any numbers yet, but I'm saying this is the true definition of an angle. Qualitatively, an angle is a portion of a circle. What portion specifically? The portion of arc length divided by the size of the radius. Divided by the size of the radius just so that we can account for the fact that bigger circles, of course, if you measure farther out, of course, you're going to get more arc length, and we're not trying to get distracted by that. So just on this alone, give me an electronic hand if you're okay so far. It's okay, that's Ashton, thank you. That's one. Wait, or no, I've lost people now. Oh, Jonathan, thank you. Okay, awesome. Giselle, thank you. Sulady, thank you. Okay. In fact, Catherine, Kayla, I'm going to go a step further just because it's so important. I'm going to say, I totally believe you, but can everybody in the direct chat, I want everybody to say something in the direct chat. Either say, yes, I'm fine, or no, you lost me, or even just say, frankly, I wasn't paying attention, and I won't shame you for it. But just tell me honestly in direct chat. Oh, okay, well, that's public chat. All right, awesome. But okay. All right, that's fair. Okay, cool. All right. I meant it to be private, but okay, fine. Awesome. Okay, now I'm embarrassed. Okay. Oh, that's good. Thank you. So, okay. So now look, how does this actually convert into radians or anything else like that? Well, remember I keep saying the whole thing about circles, is there something universal about circles? There is something universal about circles. Okay. Okay, cool. Oh, cool. Thank you, people okay, cool. Okay, so now we're going to talk about circles for a second. A circle of any size, it has a radius, right? Which is, or even, actually, I'll be even more here. Let's even do this. Any circle in the world, any circular region that you have to traverse, you got two choices with any circle. You can go straight across the circle, straight across, like assume this is a center, straight across on what we call a diameter, right? Or you can go around the full circle, right? As everybody knows, the shortest distance between 2 points is a straight line. If you're faced with a circle, you could go the shortest distance straight across the circle, or you could travel the full circle. Well, it turns out, now I know you know what I'm about to say, but you might not. I don't know if you've thought about it this way. The thing that's weird about circles is that if you were to take a tree, for example, okay, and take a string and wrap it around that tree one time, a string, and wrap it around that tree, and then put it down on the ground next to a ruler and measure that length, right? Now that length, the full arc length around the whole circle, that's called a circumference. As you know, I mean, it's called a perimeter in general for any shape. If you go around a whole shape, if specifically you're going around a circle, it's called a circumference, right? Now it's a length measurement. It's a length measurement that was made through two-dimensional space, but it's a length measurement. You take a string, you wrap it around the tree, you put the string down on a ruler, you look at how long it is. That's called circumference, right? If you were to cut the tree in half and just go straight across the tree, the direct route from one edge to the other, and put that string down next to that string is called a diameter. Everybody knows that. Now, here's the thing that you've heard a million times, but let's just stop. Like, the thing is that if you put the diameter string down on a ruler and then you put another diameter, sorry, I'm a little distracted because there's a dog in back too. No, I didn't mean it like that. I'm just sorry. I don't know if you can hear. If you put the diameter string down on the ground and you put the circumference string next to it, the circumference string is clearly longer than the diameter string. it turns out that for one particular tree you look at, the circumference will be a certain number of times longer than the diameter. Okay, that's not surprising. It won't be exactly 2 times longer than the original string. It won't be exactly 3 times longer than the original string. I mean, the circumference string will not be exactly 2 times longer than the diameter string. The circumference won't be exactly 3 times longer. It won't be exactly 4 times number. It'll be some weird number between 3 and 4 that's very hard to find on a ruler. And you know where I'm going with this. Before we get into what that number is, don't get bogged down in what that number is. The first revelation about that number is it doesn't matter what tree you pick. It doesn't matter what size circle you pick. The circumference string is always going to be the exact same number of times greater than the diameter string. Yeah, exactly. Good. Direct chat person. No, you're totally right. Okay. Totally right, direct chat. And you should definitely put that in for points. You're with me. But I am literally trying to backtrack on that. Absolutely. But here's where people get distracted. Like, so what I'm saying, okay, at least one person in direct chat just acknowledge that she knows where I'm going, or he knows where I'm going with this. I'm sure you all do. But look, let's pause for a second. Because that symbol is a Greek symbol. And I know you've all known since like 7th grade or whatever that Greek symbol stands for a very strange number that goes on forever, or the decimal expansion for which goes on forever without repeat or pattern. All these weird things that you've heard that, again, if you're anything like me, caused you to sort of shut down at some level and say, okay, this is just like math weirdness. I don't need to deal with this. But forget all the weirdness of the exact number. Forget what the number is. The first revelation, the first reason that we have a symbol for that number is that we believe it's a constant. The first thing that we're saying is it doesn't matter what size circle you ever approach. If you go around the whole circle and compare that to going straight across the circle, the ratio will always be the same. That is not obvious at all. It's just that you've heard it your whole life so much that we take it for granted. That is not self-evident that all circles would have that going on. How self-evident is it not? This is how self-evident it is not. The very number, the ratio itself, as you know, is a bizarro number that you'll never see on a ruler and never even see on a modern day digital calculator. The thing that we all know about pi, that it's this really, really weird number, like back up for a second and realize if it's that weird of a number that you can't even literally measure or see, how did we ever come to the conclusion that it was the same weird number for every single circle? Like there is something weird going on here. The big discovery, and it is a discovery. It was not like, like cavemen crawled out of the primordial soup and then we're like, past the meat. And by the way, the circumference to diameter ratio is always a constant. Like what? It's very, very surprising that a string around a tree should be exactly the same number of times longer than a string across a tree, regardless of what tree we're talking about. But that's what we're saying when we talk about pi. It doesn't matter what the value is. We're saying it's a constant value. And it gives us a huge advantage in dealing with circles. Are you with me so far? Like, okay. I might even, a part of me is tempted to show you where we get this, but depending on where we go with this, I can show you some good arguments that, wait, hold on. Something in the chat. Wait, I'm going too slow, I think probably. Wait. Oh, yes. Oh, yes. Something in the chat. Am I going to? Wow, that's awesome. Thank you. Oh, wait.
I just kind of made it up. We've done it before, so I did it again.
Okay. I totally appreciate the polite, reasonable thing that's in the direct chat. Okay, I'm going to take that to mean I should speed up. All right, I won't do the thing I was about to say, but I think you'll see in a second. Okay. I respectfully accept the respectful thing that was just said in the direct chat, and I will incorporate it. I'll go faster, but I think you're going to see in a second that you do need this for well, we'll see. We'll see. I hear what you're saying, direct chat person. Bear with me for a second. All right, here's where I'm going with this. Okay, assuming you all do know that C equals pi d, then what's my point? Then, and you know that diameter is, you know that a diameter is 2 times a radius, right? So what this means is that the circumference around a circle is always 2 pi times the radius. And then you've seen that a million times before. But if we accept that, in other words, this is the universality of circles, that there's always a certain ratio of arc length to radius, then what that means is okay, if C equals 2 pi r, then using this measurement of angles, if an angle is arc length divided by radius, then if you go around a whole circle, what people call a 360, but for reasons that are actually quite arcane and even more abstracted than anything I'm saying here, forget the 360 thing. If you go around a whole circle, right? If you go around a whole circle, then you go around 2 pi r. Right, sorry, we just said angle is arc length divided by radius. So if you go around a whole circle, you're going 2 pi r. That's your arc length per radius. So around a whole circle, we would say that ratio, that size is 2 pi, what we're now going to call radians. This is a pure measurement of angle. Radian is just the word for the pure way to measure an angle. In other words, a full circle, an angle of a full circle is 2 pi radians. Where pi, right, is approximately 3.14159, In other words, it's a little bit more than 3. If you go around a full circle, then you're going 2 pi radians, in other words, around 6 radians. 6 radians, 2 pi radians, approximately 6 radians, is the direct mathematical precise way of measuring what people will generally call 360 degrees. Okay, I'm about to tie this back. I mean, fair enough. Someone said in the direct chat. I'm actually now just about ready to tie this back to the lab and the homework. I mean, the only thing left really is to say something about cosines. But here's the first point: 2 pi radians means a full circle. It means what you would consider 360 degrees. A degree is not a standardized unit of measurement any more than a meter. A degree is not a meter or a kilogram or a second. Neither is a radian. They're both just fractions of a circle. when we talk about degrees, we're just talking about dividing the circle into 360 parts, which makes even less sense than anything I'm saying here. The only reason everybody is used to degrees is just that, because they're used to degrees, because you've been hearing it your whole life. I'll tell you another time, or maybe you can guess where the decision to divide a circle into 360 parts comes from, but it helps not at all with the lab or with the homework. What I'm saying here is, from here on in, if you think of a full circle as 2 pi radians, if from here on in you think of a half circle, or 180 degrees, as pi radians, if you think from now on as and a right angle as pi over 2 radians, pi is a number. It's essentially or approximately 3. It's not exactly, but it's essentially approximately 3. For the sake of measurement and labs and physical understanding, what I'm saying is that 6 radians is essentially a full circle. Therefore, what is a radian from now on? If you want to know what a radian is, a radian is approximately a sixth of a circle. Where did I get 6 from? Because 2 times pi is essentially 6. A radian is a little bit less than a sixth of a circle. A radian is a slice of pie that is essentially a sixth of the pie, of the pizza. Okay, a radian is a little bit less than what you would call 60 degrees. That's all a radian is. It's approximately a sixth of a circle. If you want to think of it, I'm trying to get rid of degrees in this class, honestly, and in higher level science and math. But if you want to translate back to degrees, I'm saying from now on, a radian is a little bit less than a sixth of a circle, which you can, and why again did I get that? Because I'm saying 6 radians are a full circle. Where did I get that? 2 pi radians are a full circle. So a radian, oh, sorry. Did it again. So 1 radian is approximately, it's a little bit less than 60 degrees. It's like 57 degrees. That's what a radian is. Now so a radian, I'm going to say it one more time, is a sixth of a circle. What does that have to do with the lab? What does that have to do with the homework? What does that have to do with cosines and stuff? Well, the thing is, the lab and the homeworks and everything in the rest of this course is all about cycles. It's all about cycles. So cosines allow us to map cyclical motions onto circles. We already have a math that is based on circles. That's the math that I'm developing for you here. We use this math that we know about circles. We use radians as from portions of circles and the cosines that we're going to apply to them to understand larger physical processes that happen in cycles. A cycle is just like a circle in that it could be of any size we want, but we can divide it into portions known as radians. Cosines So what I'm saying right now, I mean, to start getting to the lab, you're looking at something going back and forth, back and forth. It has a certain rate that it's going back and forth, back and forth. We can't talk about its rate in conventional terms like velocity or acceleration. We can't talk about how many meters per second this thing is going. I mean, we can, but it's really misleading and unhelpful to talk about meters per second, because at every single moment that this thing is going back and forth, as we saw in the beginning of homework 1, all the parts of homework 1 that we have gotten to, we see that at every single moment, the thing going back and forth is changing its speed and it's changing its acceleration at every single moment. If you want to talk about the rate at which something is going back and forth, the constant to look at, the regular feature, the thing that doesn't change and that is predictable, as you see in the lab and so forth, are aspects not of meters, but of cycles. We can say this thing is going faster and slower and faster and slower and faster and slower and accelerating faster and slower and faster and slower, but it's always doing, say, 3 seconds for every cycle. Or conversely, we can say it's doing 1/3 of a cycle every second. These are the kind of measurements that you're making in the lab. These are the kind of measurements that we put together to make a function. Our function, that our graphs, our relations that describe the cyclical phenomenon in the lab are going to have to be discussions of measurements based on cycles and radians rather than meters. Pause for a second. Okay, I am in class. Hold on. Wait one second. We're going to actually wait. 6 o'clock. I want to shift gears and actually start showing you how this relates to the functions that you got in the lab. Okay, but wait. Okay. All right, we're going to take. Let's take, and I'll still try to let you go a little bit early if I can. But I do respect at least one person is asking for a more direct correlation between this in the lab and the homework. And that, I promise, that's what I'm getting at. But what I honestly think is that cosines are hard for people because cosines are something that we apply to angles. And 2 things about angles. 1, I don't think most of us actually ever properly understood angles. So we didn't know what we were doing. We were taking cosines of them. But 2 is totally unclear. I'm just going to say this. We're about to take a break. But the other thing is, even if you do understand it, wait, hold on one second. Even if you do understand the angle stuff that I just explained, you might very legitimately, and I think at least one person is very legitimately saying, all right, I kind of see what all this babbling you're doing about angles. I kind of see it. But yet it's really frustrating, Yaverbaum, because you're breaking down these angles and maybe they're even making more sense to me now, but I don't see any angles in the lab at all. Like there's no angles, there's no circles in the lab. So what does any of this have to do with the lab? I mean, it's a very fair question. Not that anybody literally said that, but where we're going with this is what's happening in the lab is cyclical. We need functions that can describe cyclical phenomena. We need functions that, instead of measuring standardized units of space like meters, we need functions that look at portions of a cycle. And that's what radians do for us. And the cosine is ultimately the bridge between the portions of a circle and the application in larger space of a cycle. So cosine bridges the gap, well, just like it says here, allow us to apply the math of circles to the physics of lines in space. So the next thing I have to do is show you where these cosine functions came from that you did in the lab. I'm going to pause for, let's take, and I will still try to let you go a little bit early if I can, even though I always say not to. Let's take a 7-minute break. I'm going to turn off my camera. I'm going to stop the recording. Let's do what you need to, like what time? Like 8-minute break. Okay. So we're going to take a break. And I'm turning off my camera.